So we defined what continuous functions are. So if x and y are topological spaces, a function from x to y is said to be continuous if for each open set v and y, the inverse image along f is an open subset of x, right? So a continuous function is a function whose inverse image takes open sets to open sets. And in your homework, you proved that in the case of Euclidean spaces, or in the case of where you have functions from the real numbers to the real numbers with the standard topology, this notion is equivalent to the notion you learn in calculus. The notion for continuity you learn in calculus, okay? And you can prove that this notion is equivalent to the following. So you can check for every basis elements that the inverse image is open, right? So it's enough to check on basis elements. This is what I just said about the relationship with the epsilon delta definition of continuity, which you also proved in your homework, right? Okay, so now let's prove the following. Suppose x and y are topological spaces and let f be a function. Then the following are equivalent. So you can take these as reformulations of the definition of continuity, okay? So f is continuous to, if A is any subset of x, then f maps the closure of A inside the closure of f of A. 3, if B is a closed set in Y, then the inverse image of B is closed in X. Okay, so you can also check continuity by checking it on closed sets, right? That the inverse image takes closed sets to closed sets. And finally, and this is probably more similar to the notion, the calculus epsilon delta notion of continuity, for all points x in the domain big X, and each open set V around f of x, there exists an open set U inside the domain containing x, which gets mapped into V. Is it clear that this is essentially the same as the epsilon delta definition, but formulated in terms of open sets? This is what we usually call continuous at x, right? So for any point little x in the domain and any neighborhood of f of x in the range, you can find a neighborhood of the point x in the domain mapping into the neighborhood in the range. So the idea is that it doesn't matter how small this neighborhood that you choose in the domain, sorry, in the range around f of x, doesn't matter how small that is, you can always find a neighborhood in the domain mapping inside it. Does that make sense? That's equivalent to f being continuous, as we will prove now. So we will prove 1 implies 2, 2 implies 3, 3 implies 1. And then I will prove 4 is equivalent to 1. Okay? So 1 implies 2. So assuming f is continuous, let's prove this fact, okay? So suppose f is continuous and suppose A is a subset of X. So we want to show that f of the closure of A is contained in the closure of f of A. So that's the same as saying, suppose we have a point X in the closure of A. So we want to show that f maps X to the closure of f of A, right? So let V be any neighborhood of f of X. We will prove that V intersects f of A. And that will prove that f of X is in the closure of f of A. Okay. So if V is any neighborhood of f of X, then the inverse image is a neighborhood of X because f is open, right? It takes, the inverse image takes open sets to open sets. Remember, the word neighborhood just means open set around the specified point, right? Okay. So f inverse of V is a neighborhood of X. That means that since X is in the closure of A, that means that every neighborhood intersects A. Every neighborhood of X intersects A, right? Because I'm assuming X is in the is in the closure of A. So since f inverse of B is a neighborhood of X, that means it intersects A at some point Y. But this means that after applying f, this means that V intersects f of A at f of Y. So we have proved that any neighborhood V of f of X intersects f of A. That means that f of X is in the closure of f of A, right? Every neighborhood of f of X intersects f of A. That means f of X is in the closure of f of A. Remember what it means for a point to be in the closure? We proved this little claim that said that a point is in the closure of a subset A if every neighborhood around the point intersects A. So I'm applying that claim to the point f of X in f of A. Okay, sorry, the point f of X, right? I'm applying that claim because I have just shown that every neighborhood of f of X intersects f of A. Good, so that 1 implies 2. Now let's prove 2 implies 3. So let's go up and remind us what 2 and 3 are. So 2 is if A is an X, then f of the closure of A is contained in the closure of f of A. And 3 is that for any closed subset of Y, the inverse image is closed, right? We want to prove that these two are equivalent, okay? So we will prove 2 implies 3, okay? So suppose B is closed and let A be the inverse image of B. We want to prove that A is also closed. And in order to prove that, we will prove that the closure of A equals A. Remember that that's equivalent for A being closed. That was also a claim. Okay, so let's show that. So that's equivalent to showing the closure of A is contained in A, right? Because we always have the reverse containment, right? So let's prove that. Okay, so first of all, we have f of A by definition is A is the inverse image of B. So f of A is the same as f applied to the inverse image of B. But this is always contained in B by elementary set theory. right? So what do we have? That if X is in the closure of A, then f of X is inside F of the closure of A by just applying F here, right? But by hypothesis, F of the closure of A is contained in the closure of F of A. That's what we're assuming. That's item 2. But by this here, I can take closure at both sides. And that implies that the closure of F of A is in the closure of B. But B is closed. So the closure of B is B itself, right? So this shows that F of X is contained inside B, which means that X is contained in the inverse image of B, which we called A. So X is in A, and this shows that the closure of A is contained in A, because we started with an X inside the closure of A, and we show that that X is contained in A. So that shows that containment, which proves that the closure of A is A itself, because as I said, the reverse containment is always true. A is always contained inside its closure. So that shows that, which means that A is closed. And A was just the inverse image of B, right? So that shows that if, assuming 2, we proved that the inverse image of a closed set is closed. Does that make sense? It's a little bit of set theory. Sometimes you might get lost in the details, but you zoom out and you try to remember what you're proving, right? Does that make sense? That proves 2 implies 3. Let us prove now 3 implies 1. So what do we want to show? That if the inverse image of closed sets are closed, then the function is continuous. How would you do that? Can someone tell me immediately? We want to prove that if the inverse image of a closed set is closed, then the function is continuous. What's the natural thing to do? What does it mean for a function to be continuous? It's the inverse image of open sets are open, right? So what do?
You just look at the complements?
Look at the complement and use the compatibility of inverse image with complements, right? Some basic set theory facts. Does that make sense? So let's look how we do it. Yeah. So we want to show that the inverse image of open sets are open, assuming inverse images of closed sets are closed. So let Y be an open set in, let V be an open set in Y, and consider the complement. Let's call that B. That is closed because the complement of an open set is closed. And now this is the key elementary set theory that you use, is that the inverse image of V, namely the inverse image of the complement, is the same as removing the inverse image of V from the inverse image of Y. Right? Which is the complement of the inverse image of B. So since that is closed, this is closed, which means that's open, and that's what we wanted to show. Okay? Okay, so now we have proven that 1, 2, and 3 are all equivalent. Now I'm going to prove that 4 is equivalent to 1. Mm, 4 is equivalent to 1. Let's see. So, can someone explain why 1 implies 4? That should be relatively direct. F is continuous implies 4. So what do we want to prove? We want to prove 4, assuming F is continuous, right? So to prove 4, we have to find U, an open set U around X, mapping into an open set V that you start with. So if F is continuous, what can I do? What's U?
The inverse image of V should work.
Yeah.
Is open from
right? So if you want to prove 4, assuming F is continuous, that's straightforward because you can say, oh, for all X and each open set V and Y containing F of X, you can take U to be the inverse image of V. That is going to be open because F is continuous, and it's going to have this property as well, right? Because F of the inverse image of B is contained in V. So to go from 1 to 4, you just set U equals inverse image of V. And that works. Right? Let's see that. To go from 1 to 4, so let X be a point in X and let V be a neighborhood. Oops, sorry. Let V be a neighborhood of F of X. Then you just set U equal the inverse image of V. That's a neighborhood of F of X, and that has this property. Right? So that's straightforward. And now how do we go back? Let's look again at the items. So assuming 4, we want to prove 1. So we want to prove that the inverse image of open sets are open. That's proving 1, right? Does anyone see it, like an outline of how this should go? Assuming 4, prove that the inverse image of open sets are open.
Well, for any point in, or for any F of X and V, we have an open set about X.
Mm-hmm.
So that's a neighborhood that will be contained in our inverse image for any point.
You have that for all points, right? And then that proves that the inverse image is open because you can just cover the inverse image with all of these open sets which are contained there. So let me be more precise. So 4 implies 1. So we're assuming 4 and we want to prove that the inverse image of open sets are open. So let V be an open set in Y. And let X, little x, be a point in the inverse image of V, right? Now by assumption, since F of X is inside V, there exists a neighborhood, which I'm going to call UX of X, such that F maps U of X to V. That's the hypothesis that we're assuming. That's 4, right? So this means that U of X is contained inside this inverse image, right? U of X is the neighborhood of X inside the inverse image, right? You have the inverse image, and for all X, you have found a U of X here, right? Having that property that it gets mapped to V, right? So I can now write my inverse image as the union of all of these, because where X ranges through all points in f of V, right? Because for all X, I have a U of X which stays inside that set, right? So I can just cover that set with all of these U of X's. But all of these U of X's are open by assumption, right? That's what the hypothesis guarantees, the existence of these U of X's. So there's a union of open sets. So f of V is open, okay? So this is a good fact to have in mind, this reformulation for continuity. So take a look at it again. F as continuous is the same thing as having this condition for all points X, right? That's very important. We use it interchangeably, right? These two notions of continuity all the time in topology. So you should get that absorbed. 1 and 4 are the same. Did everyone get that? Okay, cool. Okay, so, so when you're learning, many of you have probably taken like algebra courses. And for example, when you're learning what maps between groups are, you say, oh, these are called homomorphisms, right? That preserve certain structure. And then you have a notion of kind of when two things are the same, right? Which you called isomorphism in groups. So in topology, we have a notion of equivalence, right? Of when two topological spaces are exactly the same. And that's called homeomorphism, right? Homeo is the same. Comes from the same, the equivalence in Greek, right? So homeomorphism. So what's a homeomorphism? It's basically a bijective function which is continuous and such that its inverse is continuous. That's it. So if X and Y are topological spaces, then a homeomorphism is a bijective function between X and Y, a bijection, such that both F and its inverse are continuous. Right? So you can quickly check that this is the same as saying the following. So F is a homeomorphism is the same as saying F of U is open if and only if U is open in X. Just using the fact that you have an inverse function which is continuous, right? Both F and its inverse are continuous, and it's a bijection. So what does that mean? That F does not only induce a bijection between X and Y, but it induces a bijection between the topologies of X and Y. This is exactly what this means. So if you look at X, of course, X has a topology like tau of X, right? And Y has a topology, tau of Y. So a homeomorphism is a function that it induces a bijection between X and Y, but also a bijection between these collection of subsets, right? That's what this is saying. So for all purposes, your topological spaces are the same. Its underlying sets are bijective, and its collections of open sets are bijective. So it preserves all of this, the map preserves all of the structure of a topological space. So they're the same in some sense, right? They're equivalent. Does that make sense? So bijection such that a continuous bijection such that its inverse is continuous. That's a homeomorphism. And then an embedding, it's kind of an injective version, which is like an injective map, which is a homeomorphism onto its image. That's it. That's an embedding. So let me make that a little bit more precise. So an embedding is an injective continuous function f from x to y, such that the induced map f, which I'm calling f again, from x onto its image, right? I'm just looking at the image of x and y. F induces a map of this sort, where when you equip f of x with the subspace topology, it's a homeomorphism. So that's an embedding. So this is what you have to remember or have in mind. An embedding is a injective map, which is a homeomorphism onto its image, right? Okay.
Why do you need to say that? Oh, it's not okay. It's never mind. Never mind.
Yeah. Let me remark something, actually. Look at the definition of homeomorphism. It's saying it's a bijective function such that both f and f inverse are continuous. So it turns out that there are bijective continuous functions whose inverse is not continuous. Okay, so these are not homeomorphisms. A homeomorphism is a bijective function whose inverse is also continuous.
So if you have an embedding, can you like get a homeomorphism out of it by like doing the restriction?
The restriction on the range. Yeah. So an embedding is exactly a map which is a homeomorphism from x to its image inside y, right? So this,
I guess, like, why do we bother saying that it's injective then?
Because because you want this to be kind of a copy of x. You want this to be a bijection, right? Okay, you don't have to say it then. You're saying if you say that this is a homeomorphism, then that implies that f is injective, right? Because it has to be a bijection from f to f of x. So yeah, you're right.
I'm just saying, like, when you think of an embedding, it's the minute you take the restriction, you get a homeomorphism. Is all I'm trying to say.
Yeah, but that implies that the map is injective. Do you understand why?
Because the embedding itself, y might not be f of x. Is that what you're saying?
Like, are you talking to me or?
Yeah, sorry, you, Dr. Rivera. You're saying that y might not be all of f of x.
Yeah, y might not be all of f of x in this definition. Right.
Got it.
Yeah. Okay. So there's you should know that this there's a difference with so this is for those of you who have taken some kind of algebra course. If you have a map between groups, that means homomorphism between groups, then you can prove that if that homomorphism is bijective, then its inverse, it's also a homomorphism. So an isomorphism in algebra is a bijective homomorphism. That's different from topology. Okay, and I'll give a counterexample in a minute. In other words, there are continuous bijections whose inverse is not continuous. I'll give an example now. Okay, so some easy examples of homeomorphisms? Well, kind of a linear map of this form, right? These are continuous, as you prove in calculus. You can compute its inverse, in this case given by this formula, as you learn in high school, right? And you can check that both are continuous, right? And that both are inverses to each other, right? So it's a bijection indeed. Okay. So let's do something a little bit more interesting. So it turns out that you can construct a homeomorphism between the open interval from -1 to 1 with the subspace topology induced by the standard topology, and R with the standard topology. So if there's a homeomorphism between two spaces, we say they are homeomorphic. Okay, so all I'm saying is that the open interval from -1 to 1 is homeomorphic to the real numbers as a topological space. So these are the same. As topological spaces, these are essentially the same. Does that make sense? Right? And then, of course, there are many homeomorphisms, but I described this one here. This is continuous because neither -1 or 1 are in the domain. So there are no issues here, right? There is a continuous map, and you can compute its inverse. You can compute that you can show that it's a bijection by computing an inverse and showing that this inverse is both a left and right inverse for this F, and the inverse is given by this map, which you can show that it's continuous in all of R, right? On all of R. So this F is in fact a homeomorphism from -1 to 1, the open interval from -1 to 1 to the real numbers with the standard topology. So you probably knew this fact, right? That the real numbers are homeomorphic, in fact, to any open interval, right? So, I mean, just like what happens with like cardinality of sets, you can have a topological space X, right? And you can find a subspace. I mean, it's possible to have a subspace Y, sorry, a subspace A, such that A is homeomorphic to X. That's possible, right? Because it's possible to have a bijection between sets A and X, even if one is contained inside the other, right? Of course, there's a bijection between the even integers and the integers. Anyway, yeah. So now let me give you a counterexample to what I said before. So this should be a counterexample or an example of the following. I want to describe a bijective continuous function which is not a homeomorphism. Okay? So consider the circle inside the plane R2. So the circle consists of all points X and Y. So I'm using this cross symbol because the comma symbol can get confusing because I'm talking about open intervals a lot. So I don't want to get that notation mixed up. So the circle consists of all points X, Y. such that x squared plus y squared equals 1. That's a subset of the plane, right? The circle of radius 1. And now you can put the subspace topology on S1 induced by the standard topology on R2 on the plane, whose open sets are whose basis for open sets are open balls, right? And now you can define a map, which I'm sure you guys know. You can define a function. So another comment. I'm using the words map and function to mean the same, exactly the same. Okay. So we can define a function, a continuous function from the half closed interval from 0 to 1, right? To the circle by this formula. You send a t inside the half closed interval to cosine 2 pi of t sine 2 pi of t, right? So what are you doing? You're taking this half closed interval and wrapping it around the circle like that, right? But then it's open here, right? Like, yeah, like that. Good? That's clearly a bijection of sets between this set and this set. You guys see that? It completely covers the circle, this half closed interval, right? However, its inverse is not continuous. What's the problem? I mean, that's the same as I mean, the problem is that you can find an open set U inside here such that f of u is not open inside here, right? For example, if you take the half closed interval containing 0 up to 1/4, up to 1/4, not containing 1/4, if you map it to the circle, it might look something like that, right? Open on this side. But that's not an open set in the circle. How do open sets in the circle look like? It looks like intersections of open sets in R2 with the circle, right? So all open sets in the circle should look like, let's see if I can do this. Oops, that's not a circle. That's kind of like a potato. So all open sets in the circle should look like, sorry. Should look like open intervals like that, right? Because that's what you get by intersecting with open sets in the plane, right? Open sets in the plane are things like the following. I don't know, right? So if you intersect that open set in the plane with the circle, then you get like something that looks like all points from here to here, not including these endpoints, right? So all open sets in the circle are open intervals of this sort, right? But this image here of a set U is not open in the circle, right?
This is because you have the closed bracket on the left, right?
Yeah, exactly. But this is open here, right? Do you see that? Because
yeah, like under the subspace one.
Yeah, on the subspace topology, right? So what's going on? This F gives a bijection, which is continuous, because the other way definitely works, right? If you take an inverse, if you take an open set here, let's call it V, an open set V in the circle, then its inverse image under this F will definitely be open in this half open interval. So it's a continuous bijection, but F does not send open sets to open sets. And this is the same as saying the inverse image of F is not continuous, because the inverse image of the inverse image of F is F. Did everyone follow that last comment? This fact that F does not send open sets to open sets means that the inverse image is not continuous, right? Because let's say I want to show that the inverse image is continuous. What do I have to show? That if I take any open set, then this is open as well, right? So let me use U, right? But this is the same as F of U, right? Anyway, so that's an example. Okay. Okay, cool. So let me give you some examples of continuous functions and a way of constructing continuous functions. I will not prove this theorem. It's easy. It's a straightforward check. It's in the book as well. You should read it, or you should try it yourself, or convince yourself. But it's straightforward, so you'll see. So first of all, constant functions are continuous. So if you have a map from X to Y such that F maps all of X into a single point Y, then F is continuous. Okay, maps that crush everything into a point are continuous. Okay. If A is a subspace of X, then the inclusion map that takes A and includes it inside X is continuous. Okay, that should be straightforward to check, of course. If F and G are continuous functions between topological spaces, which are composable, then its composition is again continuous, right? That follows from the compatibility between inverse images and compositions of functions, right? If you have a map F, which is continuous, and A is a subspace in the domain, then if you restrict that F to that subspace, you also get a continuous map. Okay. If you have a map F, which is continuous, and Z is a subspace of the range such that it contains the image of X, then you have an induced map from X to Z, right? Just applying F that will lie inside Z, because Z contains the image. So that map is continuous. This is also called restricting the range sometimes. Does that make sense? And finally, another fact, if F from X to Y is a function between sets which are topological spaces, and we write X as the union of open sets, as a union of open sets U alpha, such that F restricts to a continuous map on each of these open pieces, like on each of these open sets, then F is continuous itself. So this is saying that continuity is local. Is this clear? This statement here? That's important. Namely, if you have a function which happens to be continuous at each open piece of an open covering of your space, then the function itself is continuous.
So this the U alphas, because you talked about this word, is that supposed to be a subbasis?
No, I'm just saying the U alphas are any collections of open sets covering X. In fact, you can have a single U alpha being X itself. Then the statement becomes a tautology, right? Becomes f is a function is continuous if it's continuous, right? But U alpha is any collection of open sets such that its union is X. If a function is continuous at every piece, then it will be continuous on the whole thing. Assuming each of these sets is open, okay? Do these facts make sense? Constant maps are continuous, restrictions are continuous, and compositions of continuous functions are continuous, okay? I will not comment on their proof. You should read them, but they're straightforward, okay? And now an important statement. So I'm gonna take 3 more minutes if everyone is okay with that. An important statement for constructing continuous functions is the following. So this is important. I mean, it's easy to prove, but it's very useful. So suppose X is the union of 2 closed sets, A and B. Okay? So A and B are closed in X, and they cover X. Namely, their union is X. Okay? And suppose we have a function f on A, which is continuous, and a function g on B, which is continuous. So I'm thinking of A and B equipped with the subspace topology, of course, right? So if they agree, if f and g agree on the intersection of A and B, namely they define the same map on the intersection, then f and g induce a continuous function h on all of X. So you can combine them. You can combine f and g to define a continuous function, which is what you expect, right? H is f of X at all points of A, and h is g of X at all points of B. And this is well defined because I'm assuming they are the same in the intersection, right? So if X happens to be both in A and B, then these agree because of my assumption, right? So if f is continuous on A and g is continuous on B, and A and B are closed, and they agree on the intersection, then you can combine them to define a continuous function. Does that make sense? The statement, is it clear? So the proof is easy. So I'm gonna prove that this H that I have defined here is continuous. And I'm going to prove that by proving that the inverse image of a closed set is closed. Remember, this was equivalent for a function to be continuous. You can check the inverse image of open sets are open, or equivalently, you can check that the inverse image of closed sets are closed. So let me check that the inverse image of a closed set is closed in this case. So let C be a closed set in Y, and consider the inverse image of C along H. Now you have to convince yourself, again by elementary set theory, that since H is defined in this way, then the inverse image of C along H is the union of the inverse image of C along F together with the inverse image of C along G. right? You have to convince yourself of this. This is also not too hard. It's elementary set theory. Just think about it for 3 minutes. That if f is given by, sorry, if h is given by f and g in this form, then you have this, that the inverse image of h is given by the union of inverse images of f and g, right? But now, since f is continuous, you can show that, right, that f inverse of c is closed because f is a continuous function from a to c, right? So the inverse image of a closed set is closed. It's closed in a, right? Because f is a function with domain a, so that's closed in a. But a itself is closed in x by hypothesis. So that means that this is closed in x. Remember? If you have a closed set of a closed subset of a closed set, then it's closed in the bigger space. We proved this. Similarly, for G inverse of C, since G is continuous, the inverse image of a closed set is closed in the domain of G, which is B. So this is closed in B. But B is closed in X by hypothesis. So this turns out to be closed in X. And the finite union of closed sets is closed. So since each of these are closed in X, then this union is closed in X, which is what we wanted to prove, which means that H is continuous. So this is an important statement, right? You've seen it in calculus, right? It's like when you have these functions in like a first calc course, you have like functions that are like defined like, I don't know, like you have a defined by a formula here, and then you have another formula here. Then you have to prove that that function is continuous, right? So that's what you're doing. You have a closed set, right? Like maybe this is A and this is B, this is A, right? So you have two functions that agree at the intersection, which is only that point defined to be that. So when you paste them together, they induce a continuous function, right? That's the, yeah. Is that clear? There is an important fact that you will be using over and over again, the pasting lemma, right? Yeah, functions on closed sets, which are continuous on each closed set and agree on the intersection, then they combine to a function on the whole set, assuming these closed sets can cover the topological space, right? You can paste functions, continuous functions. That's what this is saying, along closed sets. You can paste them together. Okay, that's it for today. Any questions?